But I have a very basic doubt. Maybe it's pretty sure from mathematics point of view. I just wanted to ask that in the last class we discussed amplitude A1, A2, A3, and A4.
Yeah.
And also we discussed that amplitude is complex number, that A conjugate and all the things. I understand from mathematics point of view that okay, it is complex, but in practically, how can it be complex?
Yeah. So the actual electric field that you would measure has to be a real number, right? So that's why remember we started with writing the electric field as so we write it as A, then e to the time, let's say some ikz, and then we also have the frequency or temporal component, and then we write a plus complex conjugate, right? So the total electric field is given by this whole quantity. So this complex conjugate ensures that the electric field is a real number, right? And then we sort of do all our mathematics just keeping in mind A, and instead of writing the whole thing again and again, we just sort of keep track. I mean, that's the complex notation which is used in wave analysis, right? That's why it's convenient to do this. Otherwise, you have to keep, if you write this whole thing down, either you have to take the electric field as some A cosine kz minus omega t plus phi, something like that, right? And then you have to manipulate sines and cosines, which is just very tedious. So that's why we convert it to this complex notation, right?
Okay, sir, got it.
But, yeah.
Thank you, sir.
So finally, yeah, if you wanted to see what is the real value of some quantity, you add the complex conjugate to make it real, right?
Okay, sir.
So that's just this is also called phasor notation. So A is a phasor, like a complex number in a complex plane. Okay. So we'll continue from the last class. We were discussing optical phase conjugation. Right? Which you're doing via degenerate forward mixing. Right, so we discussed the concept of optical phase conjugation. So basically, you have some medium, right, and you send in some input wave, and if the reflection is proportional to the conjugate of the input, then we say this device is doing phase conjugation, right? So in our setup, what we had was so this was some type 3 material, right? And so we had two counter propagating pumps, A1, A2, and then we had a weak signal beam incident. So, and basically our task was to show that the reflected beam from here, input is signal or probe, and the reflected would be the conjugate. So basically we wanted to show that A4 will be something proportional to A3 conjugate, right? So because the direction of propagation of the signal and conjugate the z direction, then let's say the medium has extended from 0 to L. Right, and last time we had gotten so far as to find solutions for A4 and A3. So general solutions for A4 and A3. So we got something like so A4 prime right? So this A4 prime and A3 prime were related to the A3 and A4 just by some phases, right? So A4 prime was A4 times e to the I kappa 3z. A3 prime was A3. Right, so if I just multiply this whole thing by either e to the minus or plus kappa 3z, then I get A4 or A3. Right? And in the end, we'll be interested in, let's say, the intensity or the magnitude. So phase is not really important. Right, and this kappa and kappa 3 were dependent on the pump beam intensities. Right. So if you recall, so kappa here was right, where IP is the intensity of each of the pump beams. So right, and kappa 3 was this 2 times kappa. And in general, kappa and kappa 3 could be complex numbers, so they could have some phase here. Right, but the solutions depend on the magnitude. So basically, they only depend on the pump intensity. Okay, so now basically the task is to solve. So C1 and C2 are some general constants, right? And basically we would like to get values for those based on the boundary conditions we have, right? So what are the boundary conditions? So we have obviously we'll send in our input beam, which is a signal from here from the left, right? And due to the nonlinear interaction, the conjugate wave gets generated and reflected back. So of course, from this side, we don't have any input, right? Or you can say that the conjugate beam for Z greater than L, there's no conjugate beam, right? Because there's nothing there. So A4 prime at L, you can say is 0, right? So basically, there's no conjugate beam beyond this point. So we can put Z equal to L here and equate it to 0. So from that, you can see we get a relation between C1 and C2. Okay, so that's one boundary condition. The second boundary condition is basically we know the the input beam we are sending in, right? So we know, for example, what input intensity will be sending in. So basically, we know A3 at the input. So at z equal to 0, we know what A3 we send in, or equivalently, we know A3 prime or A3 prime conjugate. So A3 prime conjugate at 0, we know this is what is under our control. We are sending it in. So if you put z equal to 0 here, then you get another relation between or the stator gets C2 is equal to the input amplitude. Right, and from there we get C1.
Then we can't.
The video goes away.
Okay. Okay, so basically we can get C1 and C2 in terms of the input amplitude A3 at 0. Okay. So then we basically have a complete solution. So plugging in values for C1 and C2. So I can write A4 Okay, so now you can directly see that the conjugate amplitude is something proportional to the conjugate of the input signal amplitude. Okay, so here finally we directly see that this is somehow giving you the reflected wave as the conjugate of the input. So just simplify this a little bit further. So we write this tan as sine by cos. Okay. And then we can do that. So I can rewrite this as right. So now this is you can see of the form sine A cos B minus sine B cos sine A cos B, right? So this is sine A minus B formula. right? So sine A minus B gives you L minus Z. So that's the solution for A4 prime. So these are all constants, right? It goes as basically sine of something which is proportional to comp intensity times L minus Z. Similarly, we can get the solution for A3 inside the medium. And that goes as cosine of L minus Z, you can check. Right, so A4 goes as sine of something L minus Z, and A3 goes as cosine of something times L minus Z. So we are interested in the reflected wave, right? So basically we are interested in the conjugate generated at Z equal to 0. Right, so basically what is happening, the signal enters the medium, the nonlinear interaction happens inside the medium, the conjugate wave gets generated, then it comes out and leaves the medium from Z equal to 0. Right? So Z equal to 0, the conjugate at Z equal to 0 will be what propagates outward in space. So basically the reflected conjugate is A4 at 0. So just put Z equal to 0 here. So you get sine by cos or tan. Right? So the reflected conjugate at the input facet of the medium is equal to the input amplitude times something, right? So this something is like a reflection coefficient, right? You can also find what happens to the signal at the end of the medium. So, for example,
The video is gone off.
why? Oops. Yeah, sorry, this is annoying. I don't know. Doesn't happen from my side, but just keep prompting whenever this happens. Yeah, so A3 at L, especially if I put L here, okay, so this becomes cosine of 0, which is 1, and then 1 over cos, you can write as secant. Okay. So this equation is basically encapsulates the whole process, right? So the reflected conjugate that we get is the input signal amplitude times the conjugate of the input signal amplitude times something which is like a reflection coefficient. Right, so we can define a reflectivity, or more precisely what is called phase conjugate reflectivity. So R this subscript PC for phase conjugate. It's basically the reflected intensity of the conjugate divided by the input intensity of my signal, right? And you can see that from here that this tan square of this kappa L.
So the video again goes off.
Today it's happening more often. Yeah, so the reflectivity here you can see is tan square of this quantity kappa L, right? And kappa depends on, as we saw, the pump intensity, right? So one thing to note here is, so traditionally, like if we reflect off of some mirror or some other kind of material, usually the reflection coefficient is between 0 and 1, right? But here you can see it's a tan function which spans basically 0 to infinity, right? So the reflection coefficient can actually go 0 all the way up to some very, very large value also. So first of all, does that seem consistent, or there is something wrong, or how do you explain that? That the reflectivity can be a very large number, much bigger than 1. So like a traditional, I mean, when we do reflection of a material or some mirror, it's a passive material, right? There is no energy being pumped into the medium, and basically depending on the passive properties of the material, we get some reflection. Here you can see we have these pumps, right? So we are actually pumping energy into the medium, right?
Acting as a source.
Sorry?
Maybe acting as a source. That's why.
Yeah. So what is happening, right? So remember, go back. We started from this 4-way mixing process, right? What is happening? So energy is being transferred from my pumps. So these 1 and 2, which are the pumps, and 3 and 4 are my signal and conjugate. So I take away photons from the pump and then create photons at the signal and conjugate, right? So that's why, for example, my conjugate can be higher, or it's experiencing gain, because basically we're extracting energy from the pump. Okay. And so when does this divert? So when the argument of the tan becomes pi by 2, you know tan pi by 2 is infinity, right, or not defined. So when mod of kappa times L becomes pi by 2, and that's when the reflectivity diverges, right? And this kappa, I raised that, was basically proportional to the pump intensity. So this was right. So you can see this times, so this is like K N2I times L when it's pi by 2, right? So K times L, this is like a nonlinear phase shift, right? Or in some sense, you can think of it as a cross phase modulation imposed by the pump on the signal or conjugate, right? So when that becomes of the order of pi by 2, that's when the reflectivity diverges. Okay, and you can see that even the signal wave actually experiences amplification, right? So here, so the intensity or the amplitude of the wave, input wave at the end of the medium L is this quantity secant kappa L times the input. And you know secant is 1 over cosine, so secant is always greater than 1. Right? So the signal wave actually also experiences amplification inside the medium. Right? So both signal and conjugate are amplified, which can be explained from the fact that basically the process occurring is we are taking energy from the pumps and transferring it to the signal and conjugate. Okay, so if you look at what is, if I graphically try to see what is happening inside the medium, right? So my signal, input signal here starts from some input value I give, right? So this is A3 at 0, and then it increases in amplitude as Z increases. So it goes something like that, right? And then finally A3 at L is this secant kappa L times A3 at the input. So that's the signal wave which experiences amplification inside the medium. And the conjugate wave, so it starts from 0 at L, right? It's traveling in the backward direction. And then it goes up and finally reaches some value. So A4 at 0 here. This is A4, A3. Right, and so the reflected A4 in magnitude can be much bigger than the input A3. So that's the reflectivity. Okay, so so this should not be too hard to set up, right? Like we can, I mean, now powerful lasers are easily available, so we can always set up the pump intensities to be such that kappa L is pi by 2, right? The nonlinear phase shift here is through the medium is pi by 2. So then does that mean that we can get infinite reflectivity? So getting this condition kappa L equal to pi by 2 experimentally is not difficult. But then according to our theory, A4 should blow up. So is that correct, or did we make some assumptions in our theory that will break down? Any guesses? So again, if you look back to what is happening, right, the signal and conjugate is extracting energy from the pumps. So of course my energy in the pumps is large, but it's finite, right? So we made the, remember we started with this assumption that A1 and A2 is much bigger than A3 and A4, right? And all our derivation was based on that. So of course, if this reflectivity becomes really large, so A4 can become very large, and once it becomes comparable to A1, A2, then our initial approximation breaks down, right? That the A1, A2 pumps are much stronger than signal. So then we can't neglect, so remember initially when we were writing down the nonlinear polarization, we neglected a lot of terms saying that that's because A3 and A4 are much smaller than A1, A2, then we can't neglect those any longer, right? Then of course our solution won't be this anymore. So basically the solution is in the limit of undepleted pumps, right? So the energy transferred from the pumps to the signal or conjugate is low enough that we can assume that the energy in the pumps remains the same. But once you start transferring enough energy that you start depleting the pumps, then basically we have to take other terms into account, and then our theory doesn't hold any longer. right? So that's where the catch is.
Case of this depleted pump will cause called as saturation reason, right?
Yeah. So this we derived assuming that sort of there's no depletion in the pump. But if you take that into account, then of course you won't get right. You will get that the reflectivity would saturate to some value, even if you keep increasing the pump energy. So,
Okay, sir. Sir, just one question. Whether this amplitude of A3L and A40 will be same or somehow like little bit of difference? The highest term.
yeah, they could be
A3.
different. So you can see, so A40 is tan and A3L is secant. So they are not the same in general, right? One is
Okay.
tan kappa L, one is secant kappa. So I don't know, maybe the way I drew it accidentally. Uh, so these two will not be
Yes, sir.
equal.
Yes, sir.
Okay. Then another thing to note here is that, so let's say you have kappa L equal to pi by 2, then we see that the reflectivity can be really large. So what that means is basically any small fluctuation here, right, will be suddenly amplified and we get a big reflection, right? So basically what it says is that if I have a chi-3 medium and if I send in two strong beams counter propagating to each other, if they are strong enough such that the nonlinear phase shift through the medium is of the order of pi by 2, then actually this setup is unstable, right? Any small noise in any other direction will get amplified and you will start losing energy from your input beams into that. Okay? So basically it's saying that when I have kappa L equal to pi by 2, I don't need any inputs here. Any noise anywhere will get amplified so much that it will extract energy from the pump. So two strong counter propagating beams sent into a chi-3 medium is unstable. Okay. And another thing is that, so here we looked at all degenerate case, but for example, you could also look at when the signal has a slightly different frequency. So this could be like omega plus delta. So then the conjugate will have omega minus delta, right? And then what this will do is actually introduce some phase mismatch terms, right? So when all the frequencies are equal, we automatically got phase matching in the sense that you can see that K1 plus K2 is equal to K3 plus K4. Right? Or K1 plus K2 minus K3 minus K4 is 0. If all the frequencies are equal, then by construction it is 0. But if the frequencies are not equal, now you will see that the total delta K will not be 0. Okay, so that will lead to some phase mismatch and that will again reduce this reflectivity down from the ideal value. Okay, so this phase conjugation was implemented first way back, I think like 50 years ago in Bell Labs. They actually demonstrated sort of distortion-free imaging through a turbulent medium. They showed that using this phase conjugation effect, you can remove the distortions occurring in the path. So I posted that paper on Moodle for you guys to look at. Okay.
Yes, sir.
That's yes. Any questions, or otherwise we move on to the next topic?
So only the noise will create phase mismatch or any other condition, sir. Like if pump depletion is one case.
Yeah, I mean, pump depletion will basically, so our solution was valid in the pump undepleted case. In the pump, if you take into account pump depletion, then you have to include some more terms, right, in our coupled amplitude equations. So then the solutions will be different, right? So then you won't get this solution. So that's one thing. So the reflectivity will probably saturate to some finite value. This thing is, I'm saying that if you're looking at frequencies which are not equal to the pump frequency, then that will result in a phase mismatch, which will introduce terms like e to the I delta kz in our coupled amplitude equations. So if you go back and see, we didn't have any terms like that. So basically, it was phase matched automatically because for the same frequency, the k is omega over c times n. But if omega is the same for all of them, then you can see that by construction, k1 plus k2 plus k3 plus k4 comes out to be 0. Or minus k3 minus k4 comes out to be 0. But if the signal and conjugate frequencies are slightly different from the pumps, then you will see that the delta k will not be exactly 0, right? So then that will introduce this e to the I delta kz term into my coupled amplitude equations, which will again result in a different solution, right? And probably saturate it to a finite value.
Okay, sir. Okay, sir. Thank you, sir.
Right? Any noise which is varying as a function of time on your signal, in the frequency domain, you can think of it as extra frequency components. So yes, I mean, any extra noise would cause new frequency components to be present on your signal, which would also cause this, basically.
Sir, the paper you posted, in that it says that the pump interacts with the signal to generate a phase grating, and that acts, and then the signal interacts with that phase grating to generate the conjugate.
Uh-huh. So you can think of it like that also, yeah. So you can think of, uh, so these two counter-propagating beams create some sort of standing wave in the medium, right? Regions of high and low intensity periodically. And these pumps are causing a phase shift on the signal, right? Let's say cross phase modulation. So there'll be periodic regions of high phase shift, low phase shift, high phase shift, low phase shift, right? So it's something like a grating, right?
Moving
What is the
grating, sir.
grating? Grating is like you have periodic regions of high active index, right, which cause periodic regions of high and low phase change, which is something similar. What you think of a grating being created here, because of which the signal reflects off and creates a cone.
Kind of moving grating or something else. Hello?
Yeah.
It's a kind of moving grating or something, static grating, sir. Moving kind of, right?
Well, if the pumps, these two counter-propagating pumps are of the same frequency, then it's like a standing wave, right?
Okay.
Then it's not a moving grating.
Okay.
But the signal is moving with respect to the grating.
Okay.
There's a fixed grating in the medium, but of course, yeah.
Okay.
So a moving grating would lead to a frequency shift in the reflection. Okay, so here we see that the reflected conjugate has the same frequency, so forget about this delta. So in this degenerate case, the reflected conjugate has the same frequency as the signal, right? So so that also means that the grating has to be static. If the grating is moving, then actually the reflected, you can think of it as a Doppler shift, right? The reflected wave will have a frequency shift compared to the input. So, which is what, for example, happens in Brillouin scattering. You have a sound wave
Yes, sir.
which
Yes, sir.
creates a grating, right, and it's moving. So the reflected wave is at a different frequency. But here it's okay. So this was an example of four-way mixing here, right? So this kind of process where we annihilate two photons and create two photons, but we looked at the degenerate case. So now let's look at a more general case where these frequencies can be different. Right, so let's look at non-degenerate or maybe partially degenerate, where like let's say two of the frequencies are equal. Right, so the four-way mixing case in general can have four different frequencies: omega 1, omega 2, omega 3, and omega 4. Okay. And two of these four waves are strong, which are called pumps, right? Again, so when I denote a double arrow, I say that those are strong. So omega 1 and 2 will be pumps here. And omega 3, 4 will be weaker compared to the pumps. So one of them will be called signal. The other is called idler, or sometimes probe and conjugate. Okay, so and typically this kind of interaction is always done in a fiber or waveguide. Okay, it's quite difficult to do in free space, like just with focusing beams into a material, because you need very high intensities for it to be efficient. Right. So if in a fiber or waveguide, you recall that the electric field mode I can write as like a transverse mode profile times an amplitude, which changes as you propagate in this z direction, and then a phase which has, so instead of kz we write beta here for a propagating mode in a waveguide, and then the temporal phase is the I omega t. Okay, so I here is 1, 2, 3, 4 for the four waves, right? So beta here is omega over c times n, where now n is the effective index of that particular mode. And if you recall in our brief discussion on this previously, typically what we do is normalize the amplitude such that mod square of the amplitude gives me power. So this is watts and square root of. So the amplitude A is taken in units of square root of watts. Okay. And then if I normalize the amplitude like this, again, if you go back to our discussion on the coupled amplitude equations, we saw that we can write the equations in terms of this effective nonlinearity gamma. Okay, so this looks similar to like the free space case, right? So dA by dz is equal to, so I, we get some chi3 times the nonlinear polarization, which is the product of three terms, right? Um, so if I normalize the amplitude as square root of power, then basically that constant of proportionality becomes this gamma, right? Where gamma was the effective nonlinearity. This is basically related to the nonlinear refractive index N2, like omega over C, N2 over A, right? So yeah, for I guess take omega I. Right, and this phase mismatch factor here, right? So we'll have the product of three fields here. Each of them will have A times e to the I beta z. So you'll have beta j plus beta k minus beta L, if L is conjugate, right? And then from the coupled amplitude equations, you already have an e to the minus I beta I z for I, right? So basically this delta beta is beta j plus beta k minus beta L minus. Okay, and recall we defined this effective area which depends on this transverse mode profile. Right, like that. Okay, so this is the most general case where each of these four waves could have different transverse mode profiles, for example, right? So, like in waveguides or fibers, for example, you know, if we have different transverse modes, right? So in general, all four of these could have different modes. So then this is something like the overlap factor between the different modes, right? And of course, they would also have different betas because they have different N effectives depending on the mode. Okay, so that's the most general case. But typically, for these interactions, right, they're done most efficiently when. So if you look at the frequencies here, as we discussed, they are distributed about some center frequency, right? So omega 1, 2. So omega 1 plus omega 2 has to be equal to omega 3 plus omega 4, which means the average of omega 1, omega 2 is the same as omega 3 and omega 4. So there is some center frequency about symmetrically which these frequencies are being placed, right? And typically, so like for example at the telecom wavelengths, this would be around 1.5 micron, the wavelength, center wavelength, and all our signals will be around that. Okay, so typically it's a good approximation that all these frequencies are closely spaced, like compared to the average frequency. Okay. So then we can make some approximations in this case, right? So for the case where omega 1, 2, 3, 4 are close to each other, to some, let's say, average frequency omega, call here. Right? So frequencies close by and then typically the interaction is also efficient if they are all in the same mode. Okay, so again U1 like that. For example, they're all in the fundamental mode of the fiber, right? That's when this overlap will be maximum. So typically these two conditions are satisfied for most cases. But the frequencies are all close by compared to their average frequency, and typically their transverse mode profiles are all the same. So they're in the same transverse mode. So you can see under this approximation, basically my A effective, so all the U's are the same. So it doesn't depend on the indexes anymore. Just right. So A effective just because, so you take some particular mode profile that they are all in, and then you can compute this quantity. So integral of U square over the transverse area and square that divided by integral of U4. So that's the effective mode area which comes into the picture, into the effective nonlinearity. And now effective nonlinearity also, I don't need indices or anything. I just define an average effective nonlinearity, which is again this average frequency omega by C and then N2 divided by the C. Okay. So for all the coupled amplitude equation, the gamma coming in here will be the same. Okay. So let's look at a common case where basically the pump or the two pumps come from the same beam. So omega 1 is equal to omega 2. So basically there's actually only one pump beam. Okay, so basically omega 1 and 2 are the same, and then omega 3, 4 can be different, but they'll be symmetrically placed about my bump frequency, right? Then both of these are omega p, and then I can call this omega s for the signal frequency, omega I for the Euler frequency.
So the video has gone off.
Okay, so basically now energy conservation is 2 omega p is omega s plus omega I, or the average of omega s and omega I is omega p. So this is also sometimes called partially degenerate Fourier mixing because the pump is degenerate, right? It is coming from one beam. So this is the most common setup that is typically used for Fourier mixing: a degenerate pump and then signal and idlers symmetrically placed about the pump. Okay, and then we analyze the situation, of course, in the case These are called pumps because these are much stronger than the signal and idler. Right? So the amplitude of the pump is much bigger than the signal or idler amplitude. Okay, which again means that going back to a previous discussion on optical phase conjugation, we'll keep only the terms which are linear in AS or AI. Okay, the higher order terms in AS or AI or combination of those, we'll say are very small and can be neglected. Okay, so then we can write the coupled amplitude equations. So again, we'll have three equations: one for the pump, one for signal, and one for idler. Right. So let's start with the pump. So we have dAp by dz. Right. So let's say you have some fiber or something, and the propagation direction is z. Right. So all these three. Omega P, omega S, omega I are traveling down the waveguide of fiber. So dAp by dz will be, of course, I have this constant of the coupling, nonlinear coupling constant gamma, right? And then I'll have three terms here which have three electric field amplitudes, right? So yeah, what all terms can I get? Right, so I had AJ, AK, AL here, three. So I'm looking for something again which varies at frequency omega p, right? So I'm looking at AP, which is going at e to the I omega pt, right? So I'm looking at a product of three terms which will vary at frequency omega p. So what terms can I have? So of course, I can have omega p is equal to omega p plus omega p minus omega p, right? So that will come from 2 AP and 1 AP conjugate, right? Omega p minus omega p omega p. So that's the self phase modulation, right? And remember we had a e to the I delta beta z, but for this case delta beta will be 0 because you'll have beta p plus beta p minus beta p minus beta p. Right? So there is no phase term here, which is what we had. If you remember when we were discussing self phase modulation, this is the equation we had. Right. So if you just have this, you can see that the solution is AP is this phase, just acquires this phase, which is proportional to the intensity. But can there be other terms? So I have to
Take
choose.
the cross phase modulation term. This was the
Yeah.
self phase.
So we have cross phase modulation. So if you're looking
Choice
at
of something.
cross phase modulation on the pump, that could come from the signal or idler,
Yes, sir.
right? So you could have mod AS square AP. So that omega S minus omega S plus omega P is giving me omega P. And you'll have a 2 because of the degeneracy factor. And similarly, you could have AI, mod AI square AP. Right? But we neglect these terms because, again, we say that AP is much bigger than AS and AI, keep only linear terms. In the signal and idler amplitude. So this is square. So the cross phase modulation terms from the signal on the pump we neglect. because we're saying that the self-phase modulation of the pump is much higher than those two. Apart from that, so from here we can see that, so 2 omega p is omega s plus omega I, right? So I can get omega p as from omega s plus omega I minus omega p. You can also get omega p like this, right? So this would be as, ai, ap conjugate, right? So I could have a term like this, as, ai, ap conjugate, and there will be some phase factor here, right? Which is beta s plus beta I minus beta p. But again, we neglect this because we are getting as times ai. Right, both of these are small, so this is again quadratic in the small term. So, okay, but I hope you understand this term, right? This is apart from the cross phase modulation that signal and idler can impose on the pump, right? And actually, this looks like some four-way mixing term you can see here, right? So I'm getting product of three waves as the fourth. But okay, so basically for the pump, that's the only term we keep, and say all the others are much smaller. So this is just basically self-phase modulation from the pump. Okay, and so the solution for the pump is straightforward. The pump amplitude just acquires a phase, right? And this mod of AP square is basically the pump power, right? Because they've normalized A such that mod A square is the power. So it just acquires a phase which is gamma P, right? That's the self-phase modulation phase, right? And AP0 I can also just write like as the square root of my input pump power. Right, so the pump basically just propagates acquiring a phase, nonlinear phase. Then we can write the equation for the signal. So dAs over dz, again I gamma. Then what terms can I have here? Of course, again I could have a self-phase modulation like this, so mod As square As, but again that's not linear, right? In As, so that's small.
Right.
So what terms could we have here, which are linear in As anyway?
So from that expression now you have written 2 of omega p equals to omega s plus omega I. From there we can get the omega s signal term in terms of
Yeah.
omega.
So from here, you can get omega s as 2 omega p minus omega I. Right, so that 2 omega p's, I'll have two, so omega p plus omega p minus omega I. So I have two terms of AP. I'll have AP square, and then minus omega I is AI conjugate. And then I'll have e to the I, some phase mismatch term here. Right, so what is this? Delta beta will be, so I'll get beta p, so AP comes along with e to the I beta pz. So I'll get 2 beta p from here, then minus beta I from here, and then I'll have a minus beta s from the propagation equation for as already. So this is 2 beta p minus beta s minus beta I. I hope this term is clear. Okay, so yeah, so this is self-phase modulation. So this is actually the four-way mixing term, right? The signal is being generated using two pump photons and an ideal photon, which is conjugate or negative. Right?
One
Okay.
term would be like AP, AS, AI, something.
APASAI. How did you get that term?
Mm, normal.
So remember, we want to have a product of three terms such that the frequency variation is omega s, e to the I omega s, right?
Okay.
So yeah, one way to get them is omega p minus omega I. Is there any other way? Of course, there is self-phase modulation from the signal itself, omega s plus omega s minus omega s, but that we neglect.
Okay. Unit. Okay. It's okay.
Any other term? What about cross-phase modulation from the pump? How will that term go? So there'll be a cross-phase modulation, right? Phase shift because of the pump, nonlinear phase shift because of the pump on the signal.
Sir, AS, AI, AP conjugate.
Right, so omega s is equal to omega p minus omega p plus omega s, AP conjugate. Right, so this dA by ds is equal to something which is proportional to pump power or intensity times as. Right, it's the same thing. So here we were saying, okay, we could have terms like mod as square AP. Similarly here, we could have mod AP square as, right? So this is the cross-phase modulation from the pump on the signal. So this we can't neglect because AP is actually strong, right? And this is linear in AS. So this we keep. So this is the cross-phase modulation term from the pump. And there will be factors of 2 here because the degeneracy here, so here the degeneracy is only 3. Right, 2 of the frequencies are same, third is different. Right, and that 3 is included in this gamma here. But if you take the same gamma, then the degeneracy here is 6 because all 3. No, sorry, there won't be a 2 here, but there will be 2 there. So here again the degeneracy is only 3 because 2 of them are the same. But here all 3 are different, omega minus omega p and omega s. So the degeneracy is 6. So we get a 2. And of course you know that cross-phase modulation has to be twice of self-phase modulation also. Okay, is that clear? And then again, then go the phase there won't be any phase here because the delta beta corresponding to that will be 0, right? Because you'll have beta p minus beta p plus beta s minus beta s, so that's 0. So again, surface cross phase modulation won't have any phase mismatch. Okay, so these two terms. That's here. There is no other term which is linear in AS or AI. Okay, and varying adverse signal frequency. Similarly, we can write for the idler. So dAI by dz, again I gamma. What terms you come here?
For the cross phase, it will be same like twice of AP square.
Yeah, so this term will be same.
AI.
Cross phase modulation from the pump.
And the other term will be like twice of omega p minus omega s. So
Yeah, so we just replace S by I, right?
yes.
And this delta beta will be same, right? It's the same delta. Okay. So again, this is the photon mixing term. This is the cross phase modulation. Okay, so we already know the solution for the pump. So we can plug in AP into the equations for signal and idler and then try to solve them. So from here, when you plug in AP square, so AP square you get a PP pump power, and then this phase, and then mod AP square you just get PP pump power. So signal I can write as, so from here I get PP EI conjugate e to the I write it some delta beta prime z plus this term is just 2 PP AS. Right? And the idler is just the same, you switch I and S. So delta beta prime here is delta beta plus 2 delta beta, right? So remember we had AP square, so AP square was PP e to the I 2 gamma PP, right? And then we had a e to the I delta beta z. So when we multiplied this with e to the I delta beta z, we get delta beta plus 2 gamma p, and we define that as delta beta prime. Okay, and then similarly idler. So the equations are symmetric in signal and idler, right? So we just switch. So again, now you can see we are getting coupled equations like in the phase conjugation case, so signal is coupled to the idler conjugate of the idler. Again, idler is coupled to the conjugate of the signal, and the constant of proportion or the coupling constant depends on the pump power. Right? But now in this non-degenerate case, when the frequencies are different, we also have this phase mismatch factor coming in. Right? Okay, so again, if we had just this first terms, right, DAS by DZ equal to something times AI, DAI by DZ equal to something times AS, then we can solve them easily. But we have these extra terms, so similar to what we had in the phase conjugation case also, right? And then we did a trick of change of variables. We can do the same here to get rid of these terms coming in, right? So you can see that this is something times AS, which is coming in the derivative. So if I have e to the I this factor, then when I take that derivative, that constant comes in front, right? So we again do the same change of variable. So okay, maybe so first we just write sort of this equation in the conjugate. So take the conjugate. So just to show, so now we have basically two equations in AS and AI conjugate, right? So we do this change of variables. Okay, so the factor coming here is 2 pump power times gamma. Right? That's the factor coming in front of AS. So we take that phase factor and do a change of variables like this. And so now we write this equation in terms of B instead of A. Right? So basically here, everywhere A instead of A, you plug in B times e to the plus I 2 gamma P. So you can just see, so what happens in the signal case? So right, so I just replaced A by B times e to the 2 gamma Pz. So here you can see the left hand side we get two terms, right? So one will be and the other term will be I 2 gamma Pp. Okay. Right. So you can see that this term will get cancelled out. Right? I2 gamma Bs times e to the I2 gamma P. this term gets cancelled out. Right, so basically we got rid of this term. And we end up with something like dB by dz equal to something times, so dBs by dz equal to something times bi conjugate. Right. And the phase factor again here is delta beta minus 2 gamma p, delta beta prime minus 2 gamma p, which gives me back delta beta. Okay. No. So I have, so I'm left with e to the I 2 gamma p z dB by dBs by dz on the left hand side. On the right hand side, I2 gamma is pp bi conjugate e to the minus 2I gamma pp delta beta prime. Right. So I need to get rid of this phase. So I multiply by e to the minus 2 gamma pz on both sides. Right, so here I get 4 gamma pz. So here the phase will be delta beta prime minus 4 gamma p. Okay, and delta beta prime minus 4 gamma p will be delta beta minus 2 gamma p. Okay, so if I write that equation here, so dBs by dz bi conjugate e to the I call this delta beta total z, where delta beta total is equal to delta beta prime minus 4 gamma p, which is delta beta, the original one, minus 2 gamma. Okay, so the effective phase mismatch which is showing up here is sort of the original phase mismatch delta beta, which is just due to the refractive indices. Right, that's just the difference in the. So this was 2 beta p minus beta s minus beta I. So that's just the difference in the wave vectors due to the difference in the refractive indices at those frequencies. And then there's an additional factor coming in here, you can see, which is something like the nonlinear phase shift, right? Gamma p times L gives me the nonlinear phase shift. So this is like the nonlinear or the correction to the phase mismatch coming from the nonlinear phase. Okay. So similarly, I'll get the equation for the idler in terms of the B variable. Right, so bi conjugate okay, so we get these two coupled equations now in Bs and Bi conjugate. And this is similar to what we ended up last time with A3 prime and A4 prime, right? So, except only the change here is that we have this phase factor here. Okay, again, so now we know how to solve this. So if we differentiate the first equation once again, so right? And then we put d bi conjugate by dz like this. Oh, so I get two terms, right? So one is this, but then this term also depends on z. Okay, so this dbi by dz, you can put that, and then this other bi, this factor I gamma p bi conjugate e to the I beta z, that's just this, which is d beta z by d beta z dbs by dz. Right. So basically, I want the entire equation in terms of only one variable, bs in this case. Right. So all the bi terms, I want to convert it to the bs. Right. So you'll get a second order differential equation. Okay. So in the previous phase conjugation case where all the frequencies were degenerate, basically this middle term wasn't there. Right. In effect, this phase mismatch wasn't coming into the picture, so we just had some p square v equal to something, and then we solved. But here now we have an extra term. Yeah. Okay, similarly, if you write the equation for idler, it will be the same equation. You can check. So if I am writing for bi conjugate, then I get a plus here. Okay. So then how do we solve this equation? You must have seen this kind of equation before somewhere, right? Like for example, a damped simple harmonic oscillator. Okay, so one way to solve this equation is treat this like a quadratic equation. Okay, so if I can write this as a product of two linear terms. Okay, or like I operate two linear operators one after the other to get this second order operator. So if I write it like this, then you can just by inspection see what A1 and A2 should be to get this. Okay, so just like a quadratic equation. So I call this operator D1, call this operator D2, and these operators commute basically, right? So A1 and A2 are some constants. So you can either differentiate with this first and then this, or this first and then this, doesn't matter, right? So basically, the two solutions are either D1 of BS is 0 or D2 of BS is 0. And in general, the general solution will be a linear combination of these two solutions. Right? I'll have two linear differential equations whose solutions, if I take the linear combination, would be the general solution. Okay, so the solution to this, so the solution to this would be just something which goes as e to the I or e to the A1z. This one will be e to the A2z. Right. So the general solution will be something like C1 e to the A1z plus C2 e to the A2. Right? Right. So A1, A2 are related to these constants. So you can see A1 plus A2 has to be I delta beta total. Just like a quadratic equation, A1, A2. Right. So from these, you find out what is A1 and A2. From that, you get the general solution. Equivalently, you can assume a solution e to the Az, right? Which, for example, in a simple harmonic oscillator case or something you would have seen, right? And then plug this solution into this equation. So you get the d by dz terms will give you terms of A, right? So you'll get A square minus this times A minus this equal to 0. So you get a quadratic equation in A, right? So you get A square quadratic equation in A, whose two solutions are A1 and A2. Right? So again, my general solution would be C1 e to the A1z plus C2 e to the A2z. Okay? So either you assume a solution like this and then find the possible value of A, or you do this sort of linearized quadratic equation as a product of linear equations, and same thing. Okay, so what are A1 and A2? You can see A1 will be, so just like there will be the quadratic equation solution, right? So A1 so you just use the quadratic equation formula. You can write this as Okay, so it has an imaginary part and plus, let's say, a real part, but depending on the relative values of this delta beta and gamma p, it could be imaginary also or real. Okay, so I denote this as G. And then write this as okay. So this G is related to some gain factor. See, that's why it's called G. It's square root of gamma p square minus delta beta beta. Okay, so yeah, maybe just mention it here. So G equal to this is called the parametric gain factor. Okay, parametric is because this process is parametric. Gain, we'll see this comes in as a gain for the signal or idler. Okay, it's called parametric gain factor. Right, so the general solution then I can write for the signal and idler. Right, so B as the amplitude of the signal. The general solution I can write like this. Right, where A1 and A2 are given by these. So basically this phase part is common. So I think this will write it like this. Okay. Similarly, the idler VI conjugate I can write as CI1 conjugate. Okay. So now the task again is to find these constants
Sir, can you
CS1,
please check the video?
Okay. Yeah, again, so we need to find these constants C1, CS1, CS2, CI1, CI2, which again will depend on boundary conditions. Right? But the general form you can see goes as e to the this GZ, right? So this is like an exponential gain, right? So if G is real, then the signal is exponentially increasing with distance, right? So this G is something like a gain factor. So it's called a gain. So for example, if G is large, then this second term will be small. E to the minus GZ will eventually become very small, right? If G is large. So you can just neglect that and you can see that it will be basically exponential gain. So this G, so delta beta total, remember, was the original delta beta minus this nonlinear phase due to cross phase modulation. So if I put that into here, So I get some a square minus b square. I can write that as a plus b times a minus b. Okay. So you can see basically I can write this as in terms of the original phase mismatch, delta beta like that. So delta beta by 2 times 2 gamma p minus delta beta. Okay, so the delta beta depends on, for example, what waveguide you're choosing, how the refractive index varies with frequency, etc. Right? So the dispersion of the waveguide or the fiber. So if you plot this G versus delta beta, so you can see at delta beta equal to 0, G is actually 0. And again at delta beta equal to 4 gamma p, it is 0 again. In between, it's some real quantity. And beyond those, like at less than 0 and greater than 4 gamma p, it's imaginary. Right? So get some feature like this. So it is 0 at 0 and 4 gamma p. Right? And it peaks at delta beta equal to 2 gamma p. And the peak value is also gamma p. Right, so it's a little bit, I guess, different to the case where. So initially, remember when we were discussing nonlinear interactions, and then we said that okay, in the undepleted case, we get the sinc squared function as a function of phase mismatch, right? So we plot it as a function of delta k. We get some sinc squared and peaks at delta k equal to 0. Right, so we wanted to make the phase mismatch basically as close to 0 as possible. But here you can see that the gain is actually peaking at a finite value of the phase mismatch. Right? At 0 phase mismatch, actually the gain is 0. It peaks at some finite value and then drops again. Okay? So actually what is happening is this extra term here, right, 2 gamma p, that is basically causing this shift. And that is coming, if you go back and see, is coming from the cross phase modulation. Right? So it's the pump is adding an extra nonlinear phase to the signal and idler, which is, yeah, it's adding an extra phase which looks like an extra wave vector, right? So you have to compensate for that nonlinear phase shift, which you get by having this finite delta beta. Okay. So what is happening is basically if your actual delta beta is 0, if your phase mismatch actually you make it 0, your process is inefficient because of this nonlinear phase shift which takes it away from the phase matching, right? So to get total phase matching including the nonlinear phase, we actually want a slight phase mismatch in the original case. Another way to look at it is if I plot G as a function of delta beta total, which is delta beta minus 2 gamma p. Right, so if I plot this axis as delta beta total, then this is peaking at 0. Right, this is minus 2 gamma p, and this is plus 2 gamma p. So in the delta beta total axis, it actually looks like my original delta k. Right, I want delta beta total equal to 0. But that delta beta total includes this nonlinear phase, right? So that's basically one important outcome here. Okay, so basically in this range, if your delta beta is in the range from 0 to 4 gamma p, so one thing to notice is first delta beta has to be of a particular sign, right? So it has to be positive. So remember this delta beta was 2 beta p minus beta s minus beta I, right? So this is omega p over c times n effective at omega p, omega over c times omega s over c times n effective at omega s, etc. Right? So it depends on the dispersion of the waveguide and your medium. So in general, depending on how those properties are, this could turn out to be positive or negative, right? But you can see that for the process to be efficient, if you want good gain, then it has to be positive. This quantity has to be positive. So the dispersion has to be of a particular sign, right? If it's the opposite sign, then you end up here where G is imaginary and you don't get any gain. Okay? And it also has to be within a particular range. So if it's too large positive, then also you get into the range where it has to be between 0 and 4 gamma for this G to be turned out real and to get exponential gain. Okay? So yeah, maybe we'll stop here and continue next time. Right, to see how like solve the actual expressions and see what are the expressions for the total gain and how you can use this for amplification, all optical amplification and wavelength conversion, etc. Okay. Yeah, so we'll do that next time. We won't start now because then can't finish.
Excuse me, sir.
Yeah.
Sir, well, going to the SBS mathematics also, we are getting the same plot and the same calculation also. So, are these two things are the little bit similar only?
I mean, there are similarities, but there are differences also. So one thing is like fundamentally SBS is a non-parametric process. Okay, this is a parametric process. So basically, the total energy in the fields remains conserved, right? You are just transferring energy from one particular frequency or field to others. Whereas in SBS, part of the energy is taken away by the phonons in the medium, right? So the total energy in the optical fields is not conserved, so it's a non-parametric process. So what basically that means is effectively it's like an imaginary chi3. So here basically the chi3, so the gamma here is a real number, right? So this gamma is proportional to n2, which is proportional to chi3. So that chi3 is a real number, which gives me a real gamma. So a parametric process is defined by a real chi3. Non-parametric process like SBS turns out it's effectively like a imaginary value for the chi3, right? Something like 2 photon absorption we saw. Right? And Raman scattering, Raman and Brillouin scattering, SBS and SRS, they're both in that category. But you're right, like finally when you write sort of the coupled amplitude equations, the form is somewhat similar, right? But there, for example, the G
So
depends on.
there also
Sorry?
gain is the exponential function, right, sir? When we write the
Yeah, so
solution.
there also you can get, if you have the conditions right, then you can get exponential gain. Yes. But like the range over which, so here, for example, the range over which you can get gain is very different here because that depends on the dispersion of the medium. There, the range over which you can get gain is sort of determined by your acoustic phonon mode. Like it has a particular phonon has a particular lifetime and it which corresponds to a particular line width in frequency. Okay, so that sort of gives you the gain bandwidth, etc. But here, sort of the gain bandwidth is coming from the dispersion properties of the medium. Okay. So typically, like this kind of Fourier mixing process would be much more broadband than SBS. SBS is much narrower spectrum.
Okay, sir. Thank you, sir.
But yeah, some general features are similar. Yeah. But I mean, this is like a general feature of any amplifier, right? Even like in a laser, you have some gain medium, you pump, you create some population inversion, and then the field inside the cavity experiences exponential gain, right? So any amplifier in general would have this kind of feature, right? So this is also an amplifier which is based on this nonlinear optical phenomenon. So the gain factors, etc., depend on the nonlinearities. So in the SBS case, they depend on the Brillouin nonlinearities. But yeah, you can sort of categorize all of them under amplifiers.